All right, let's get started. And currently we are discussing about, and again, I quickly need to make sure that my slides advance. All right, so currently we are discussing about the execution engine, and more precisely, we're discussing about how the standard operators for data processing are implemented. And the relevant chapter is still Ramakrishnan and Gerke, chapter number 12. So we have discussed about a couple of operators for filtering and for joins in the last lecture. For joins, we have been discussing about those nested loop join variants, which typically have two nested for loops that iterate over the two input relations, and then they try to find matching tuples. Now in this lecture, we're going to discuss about two more join operator implementations. They are very, very popular in practice and are, for instance, also implemented in the Postgres database system. Now, those join operators, they apply in cases where our join condition is an equality between columns, which is perhaps the most typical case in practice. Last time I asked you to think a little bit about what we could exploit in order to make joins more efficient in those cases. And the first possibility that we can exploit is to use hashing. Now, the first new join that we will discuss today, that is the hash join, which uses a hash function in order to speed up the join. So we are now focusing on equality join conditions. That means we want tuple pairs which have the same value in the join column. And of course, if they have the same value in the join column, it means they also have the same hash value in the join column for an arbitrary hash function. So we exploit this as follows. Now the hash join has two phases. In the first phase, we essentially partition all the both input tables using the hash function. So first of all, we essentially make one pass over both input tables. Then we apply the hash function in order to partition that data into buckets that are associated with a specific hash function values. And we try to partition the data into sufficiently small partitions such that one of those partitions fits into main memory. That's what we need. Because in the second phase of the join, we will go over those hash value buckets one by one. And for each bucket, we will load one of them entirely into main memory in order to join the corresponding tuples separately. We can do that because since we are looking for tuples with the same value in the join column, they must be located in the same hash bucket. This is what the join exploits. Now that is the high-level overview. Now let's see some pseudocode. For that, I introduced some new notations. First of all, quite intuitive, the hash function, which calculates the hash function for a tuple in the join column, of course. Then I introduced the full predicate, which essentially tests whether one page is completely full and has no more space left for insertions. And then I introduced the write and clear function over here. So that is used for the output buffers. And it essentially does two things. First of all, it copies the current content of the output buffer to hard disk. And then it erases the content of the in-memory buffer such that it can consume new entries. All right, and with those notations and the ones that I have introduced the last time, this is the pseudocode for executing phase one in this example join between the enrollments and the students. And we want to find pairs of tuples where the student ID is the same. So here, first of all, we are going over the pages of the enrollment table, and we are sorting, we are partitioning those tuples using the hash function. So here we go over the pages of the enrollment relation E. For each page, we load it from hard disk, of course, and then we iterate over the tuples on that page, which we have just loaded. For each tuple, we are adding it. We are essentially copying it to the output buffer that is associated with the associated hash value. And if the output buffer becomes full, then we clear it and write the content to hard disk. So first write the content to hard disk, then we clear it, of course. All right. So this is the first phase of the join in which we partition tuples by the hash function. We apply it here to the enrollment table. We will see the student table in a second. Quickly reasoning about the cost. So this load page command that is invoked once for each page in the enrollment table. And the other one here, the write and clear command, also writes one page to hard disk. So that also costs us something. And since we just partition the data, the size of the input is the same as the size of the output, which means that this one, the second call, is also executed once for each page in the input table. Right? So we have said that we measure cost only by the number of pages that have been read or written to and or from hard disk. Right? So in this case, the cost is simply 2 times the number of pages in the table that we are partitioning. Now here I'm partitioning the enrollment table. I also need to partition the other one. That is the student table. That is the correct slide. So here I'm simply doing the same thing that I did before, but for the student table. Iterating over the pages, partitioning them by the hash function, and writing those output buffers to hard disk whenever they become full. All right. So now I have partitioned both my input tables by their hash function in the join columns. Now in the second phase, I'm treating each hash bucket one by one. So I am iterating over the possible hash buckets. And for each of them, I'm loading entirely the associated tuples from one of the 2 input relations. So here I have decided to entirely load the pages for the current hash bucket for the enrollment table. And after I have loaded the complete hash bucket for one of the input relations into main memory, then I'm simply iterating over the pages from the other table one by one. Here I'm iterating over the pages from the student table. And I only need to consider those pages from the corresponding hash bucket that is associated with the current hash value. And then for all the tuples that I have in main memory, I compare them and I evaluate the join condition. I still have to do that because just because 2 tuples belong into the same hash bucket, it does not yet mean that they have the same value in the join column, because typically multiple values get hashed to the same value. All right, and then I simply output the tuple pairs that match together. Okay, and here there's a great question in the chat. Okay, and there's also a great answer in the chat. Okay, I quickly address that. So the question was, we have said that we typically don't count the cost for writing out the output of an operation, because it doesn't really help us to compare different implementations for the same operation, because the output is always the same. Now, in this case, we have counted cost for writing something back to hard disk. Now, the difference here is that what we are writing out is not the final result of the join, but it is just an intermediate result. So if you compare the hash join, for instance, against the block nested loop join, that one doesn't write out some intermediate result which partitions the data according to hash value. So that's why when comparing this join operator to other join operators, we want to count the cost for writing out those intermediate results, but we do not want to count the cost for writing out the final result? Great question. All right, so in the second phase of the join, we join each hash bucket separately, and afterwards we produce the complete join result. And if you look at the cost, then the first command that is executed for each page in the enrollment table, and the inner one is executed for each page in the student table. So maybe it makes sense to have a second look to verify why that is the case. But of course, each page of the student table can only be in one of those hash buckets. So if I count together all the times that this command is invoked, then still I come back to the number of pages in the student table. All right. And this is why the total cost of this is essentially the number of pages in both the input tables. And I don't count the cost for writing out the result of that. Now, let's quickly think about how much main memory we need for that. So we will be discussing a lot about main memory consumption today, because together with runtime, that is a very important metric in the context of large-scale data processing. So for this join operator in the first phase of the join, we first of all need to reserve one page in my buffer pool, which, as a little reminder, is the part of main memory reserved for the database management system. So I need one page in memory to store the current page for partitioning. And then I want one output buffer for each of the hash buckets. So as we will discuss in more detail later, the more hash buckets I want, the more pages in main memory do I need to reserve for this first phase. In the second phase, I want to store all pages from one hash bucket from one of the relations. So in order to minimize main memory consumption, I typically want to choose the smaller table for that. And also I need to count one page for the current page from the other table, and then I still need one output buffer. So here the number of hash buckets plus 2, basically. That's how many main memory pages I need. Now, there's a couple of constraints in terms of how much main memory I want at least, let's say. So first of all, in the first phase, I essentially want like one more page than the number of hash buckets. Also, in a second phase, in order to be able to load one partition entirely into main memory, I need to make sure that those partitions are small enough in order to fit into main memory. Now, if I assume a perfectly uniform distribution of data over hash buckets, then I can say that the size per hash bucket is simply the number of pages, let's say in the smaller table, divided by the number of hash buckets. That is the expected size of one of those hash buckets. And therefore, in the second phase, I want to make sure that the expected size of one of those hash buckets plus input buffer and output buffer plus 2 is smaller or equal to the amount of main memory that I have. And as you can verify by some calculations that I won't do here, but there is a rule of thumb that makes sure that those two conditions are satisfied. And this is that we want that the amount of main memory available is a little bit greater than the square root of the number of pages in the smaller relation, right? So if you have a number of hash buckets that corresponds to the square root of pages, then your expected size of the of each hash bucket is a total number of pages divided by the square root, and that again is the square root of the pages. So if you insert this, then both of those conditions, they approximately check out. So that is the rule of thumb, how much main memory you need for the hash join. This is a little example here, the same example that we have been using for the nested loop joins. And here we are joining the enrollment and the students page tables with 1,000 enrollment pages and 100 student pages. And let's say that we have 11 buffer pages available. So the smaller input table is the students here, and it has 100 pages. So the square root of that is 10, which is a little bit smaller than the amount of main memory that we have available. So seems okay. And then the cost of this join, that is simply 3 times the size of both inputs combined. I have in the first phase of the join, I'm reading everything once and writing everything once. In the second phase of the join, I'm just reading everything once. And even if I would write out something, then I wouldn't count that cost because it's the final join result. You see the calculations in a little bit more detail, but we're just applying the formulas that we have seen on the previous slides. Now, I have described the rule of thumb about how much main memory you typically want for this join in order to execute it. If you have less main memory than that, you can of course always use a different join operator, which might be less memory hungry. Or there's also ways to adapt this join operator to deal with smaller amounts of main memory. Now, if we have not enough main memory, the problem is this. During the first phase, I need to reserve 1 output buffer in main memory for each of my hash buckets. So if I have less main memory, I will have less hash buckets, and that means that each hash bucket contains more data. And that creates a problem in the second phase because I cannot fit 1 entire hash bucket into main memory anymore because they become too large. Now, what I can do in those cases is that I don't execute 1 partitioning pass over the data, but that I execute multiple partitioning passes. So in each of those follow-up passes, I divide data in 1 bucket into sub-buckets, so to speak, which of course means that I need a different hash function. So instead of partitioning everything in 1 pass over the data, I would partition things into more and more fine-grained buckets by iterating over the data multiple times in the first join phase. And after enough passes, I can also say that in the second phase, I have reduced the size of those hash buckets enough such I can fit 1 of them entirely into main memory. So that is a possibility, but of course the join becomes less efficient because I need to make multiple passes over the data, so I need to read and write it multiple times. So at some point, it might become interesting to use one of the other join operators instead. And that is a great question here. What is basically by how much is it recommended that we decrease the size of those buckets in each pass over the data? Well, that's a great question. You essentially want to maximize the effects of those passes over the data. You want to partition data as quickly as possible. So that means that in each pass over the data, you probably want to divide everything into the maximal number of sub-buckets you can. And if you have B buffer pages available, that always means you need 1 input buffer, and that leaves you with B minus 1 output buffers. So this is the number of sub-partitions that you probably want to create. So as much partitioning as possible per iteration. All right, so that was the hash join, one of the most popular join algorithms and heavily used in database management systems. Now in the following, I'm gonna introduce 1 more join, the sort-merge join, which also applies to cases where I have an equality join condition. And that is also a very popular join operator. Also, this join algorithm executes 2 passes over the data. In the first pass over the data, we sort the 2 input tables according to their value in the join column. And then in the second phase, we use those sorted tables in order to merge them together and quickly identify tuple pairs that have the same value in a join column. So that is now much faster because I have previously sorted the two input tables. And by the way, in some cases, I might already have a table sorted beforehand. And then, of course, the sort-merge join becomes particularly interesting because you might be able to omit one of those sort operations in the first phase. In the following, we're going to assume that both of the input tables need to be sorted first. Now, you probably have heard a lot about sorting algorithms already. There's many sorting algorithms available. The problem is that most of them assume that we can access single entries in the data that I am sorting. Now, if I would do this with data that is located on hard disk, it would actually be very inefficient to jump back and forth between different single entries in that data, because as we have seen, those storage media, they often have some overhead for accessing specific locations, for instance, on hard disk. So random data access is efficient. This is why we rather want to access data in chunks, in pages of entries instead. And in order to make that efficient, you want some specialized join algorithm which takes that restriction into account. And those are called the external sort algorithms because they assume that the data to sort is not stored in main memory, but somewhere outside of main memory, meaning, for instance, on hard disk or on some flash device or on tape. So there's, in each case, on some medium that doesn't make random access very efficient. Now in the following, we're going to see a sorting algorithm which takes that into account. Now, this sorting algorithm proceeds in multiple steps. In each step, we iterate over the data and read the data once and write the data once. Now, each of those steps sorts the data more until finally all the data is sorted. In the first step, we simply do the following. We, assuming that we have a certain number of main memory pages available, we just fill all of our main memory with data from hard disk, and then we sort it in memory, and then we write the sorted version back to hard disk, potentially overriding the original unsorted data. Then so after this first step, we have multiple sorted chunks of data. We also call those sorted chunks of data runs, sorted runs. In the following steps, we are always merging together multiple of those sorted chunks in order to generate larger sorted chunks. We only can merge a limited number of chunks of runs in each step. So that means we might have to execute multiple steps until we have merged together all the data. And at that point, we get one completely sorted data. And after we have achieved one big sorted run, then we are done and the data is completely sorted. So let's see the first step in a little bit more detail. So we have B buffer pages available. We typically use the constant B in the following to designate the amount of buffer pages. So we load chunks of size B into our buffer, and then we sort the chunk via some standard sorting algorithm because now we have the data in main memory. And after we've done that, we write the sorted data back to hard disk where it forms one of those sorted runs. Let's see this by an example. So here I assume I have the hard disk content in the lower part of the screen, and in the upper part of the screen, I have the buffer pool. And as you see, which is typical, the buffer pool is of course smaller than the hard disk. Now in this first step of the sorting algorithm, I am first of all focusing on the first few pages of my hard disk content, which represents one of the two input tables to the join. And I'm loading that data into my buffer. So here the data is unsorted, as you see. So let's sort it by a standard join algorithm, by a standard sort algorithm in the buffer. And now I have sorted data in the buffer. I'm writing it back to hard disk, overriding the previously unsorted data. All right, now I've written it back to hard disk. Now we load the next chunk of data into our buffer. We sort it in our buffer and we write it back to hard disk again. All right, so this is my second sorted run on hard disk. Now I'm loading the next chunk of data. Again, I'm sorting it. I'm writing it back to hard disk. I'm doing the same thing for the last chunk of data, sorting, writing. And now on my hard disk, I have 4 sorted chunks of data, and each of those chunks has length 3, of course, because this is the maximum number of pages that I could fit into my main memory. All right. Okay, so this is the first step. It produces a certain number of sorted runs. Now in the following steps, I'm merging those runs together in order to produce larger sorted runs. Now I can only merge a fixed number of runs in one step. More precisely, if I have B buffer pages, I can merge B-1 sorted runs, and it will become clear in a second why that is. So for each of those sorted runs, I need to reserve one input buffer in my buffer pool. So that means if I want to sort together, merge together B-1 runs, I need to reserve B-1 pages. And among all the data that I have in main memory, I'm identifying the minimum entry now, and I'm copying that one into an output buffer and erase it from the corresponding input buffer. So the output buffer, this is where I'm using up my last buffer space page, because I need to write things into the output buffer before I'm writing them to hard disk. Now, whenever the output buffer becomes full, then I'm writing it back to hard disk and I clear the contents. Whenever my input buffer becomes empty, then I'm loading the next page from the corresponding sorted run. So each input buffer is associated with a different sorted run. And so if one of the input buffers becomes empty, then we load the next page from that same sorted run into the input buffer. And since those runs are sorted, I know that I am receiving the entries for each run in increasing order. All right, let's see this by a little example again. So here we assume that we have previously executed the first step of the sorting algorithm. So we have 4 sorted chunks of size 3, and now I'm merging them together. So here I have B equals 3. That means I can together merge B-1, meaning 2 sorted runs in each step. And here in the buffer pool, you see I have already written the function for each of the spaces in green. We have 1 input buffer for the first run, 1 input buffer for the second run, and we have 1 output buffer, right? So we start by loading the first page from the first 2 sorted runs, and the sorted run begins at the leftmost page and ends at the 3rd page from the left, and the next one starts from the 4th page from the left and goes until the 6th page from the left. All right. So those are the first pages of the 2 sorted runs, and now I'm loading them into the corresponding input buffers. Now I identify the smallest entry in my buffer pool, and that would currently be 1. So I'm copying that entry to the output buffer and I'm erasing it from the corresponding input buffer. This is what I have done now. Now the next smallest entry, that would be entry number 3 over here. So I'm copying that to the output buffer and erase it from the corresponding buffer. Now at this point, my output buffer has become full. So here I assume that I can only fit 2 entries on each of those pages. So since the output buffer is full, before I can continue, I first of all need to save its content to hard disk, and I need to erase it so it can accept more entries. Of course, in principle, I could also write the output buffer to hard disk before it is completely full, but you don't want to do this because each time that you're writing something to hard disk, you're paying with overheads. So I only want to write the output buffer content to hard disk when it is absolutely necessary. And in this case, it is. So let's write the output buffer to hard disk, and now we can clear it so it can receive more entries. And at this point, the smallest entry in main memory, that is 4, so I'm copying that into the output buffer. And at this point, the input buffer number 2 has become empty. So now I'm advancing the corresponding focus page in the second sorted run to the next page, and I'm loading the content into my buffer. Now, among the remaining entries, the 8 is the minimum. So I'm copying that one from the input into the output buffer and erase it in the input buffer. Here again, my output buffer has become full. So I'm copying that to hard disk and erase the output buffer in memory. At the same time, my input buffer number 1 has also become empty. So I'm loading the next page from the first sorted run. And at this point, the smallest number in main memory, that is 9. So I'm copying that to the output buffer. Next one would be 10. And here my output buffer is full, so I'm writing it to hard disk. Also, my input buffer had become empty. I'm rewinding to show that to you. So input buffer number 1 is also empty. So I'm copying the output buffer to hard disk. At the same time, I'm loading the next page from the first sorted run. All right. And now the smallest number would be 12 again, then 14. And at this point, you probably see where this is going. So I'm not going to complete the example. But if we do, then we have completely merged the 2 first sorted runs from the input. And then we are merging them into one sorted run that has now twice the size of the input sorted runs. Okay. All right. And there's a couple of questions. All right, and a couple of answers. Yes, we are merging the 2 sorted runs. So the output that I'm generating here, that will become a full merged sorted run, which contains all the elements from the first 2 sorted runs and combines them into one sorted run. Okay, and there's a question about why not put the first page of the third sorted run instead of iterating through a run. Does it matter? Okay, and that is a great question. In fact, it does matter because you essentially rely in the algorithm on receiving tuples in the input buffers in increasing order. So if you switch from a page from one sorted run to a page from a different sorted run, then the entries on that other page might be larger or smaller than the ones that you have been treating before. But this algorithm here essentially assumes that at any point in time, it always has the minimum entry in main memory that hasn't been written out to hard disk yet. And in order to make that assumption, it requires that for each of the input buffers, I'm receiving the sorted runs, the entries from the corresponding run in ascending order. So it would be a violation of the assumptions that the algorithm is based upon if in one of those input buffers, I would first have a larger number and then later would have a smaller number again. Because at this point, the algorithm has already written the output buffer to hard disk, and it would assume that it doesn't have to go back and change anything anymore. So we can only merge together sorted runs. And in this case, since we have 4 sorted runs initially, it would mean that we need actually 2 passes over the data until we have merged everything. So as a summary, we have 12 pages, and we have that we need to sort, and we have 3 buffer pages. The first step produces 4 sorted ones of length 3, and then I can merge together 2 ones in each of those merge steps. So the second step, which I have shown you, at least the beginning of it, it takes 2 sorted ones of length 3 and produces 1 sorted one of length. So the second step takes runs of length 3 and produces runs of length 6. And the third and final step takes 2 runs of length 6 as input and produces 1 run of length 12 as output, and that integrates all of the data that we wanted to sort. So after this third step over here, we are done. And yes, there is some connections to bottom-up merge sort indeed. All right. So if we analyze the cost of that phase, we have to execute multiple sorting passes, and in each of those passes, we read and write the data once. So if n is the number of pages to sort, then the cost per pass is 2 times n, reading and writing. Now, the interesting question is, how many passes do I need to make until all the data is sorted? And we can think about the length of the sorted runs that I'm producing, because if that length reaches the entire data set, I know that I'm done. Now, after the first step, we have sorted runs of length b, which is the number of buffer pages. In the second step, I'm merging b-1 sorted runs together. So the length of the output run multiplies b by b-1. In the third step, in all following ones, I'm also merging together b-1 sorted runs. So the length always multiplies by that factor. And therefore, once the length of those runs as a function of the number of steps executed has reached or exceeded the total number of pages, then I know that I am done. So you have the formula here on the bottom of the slide. And if you resolve that towards the number of steps by taking the logarithm on both sides, then you end up with a formula that depends logarithmically on the number of pages. All right. So that is the first phase of the sort-merge join, where I'm sorting the input relations. And now I assume that I have both input tables sorted by their values in the join column. So after that, it becomes quite efficient to merge them together in order to produce the join result. So we proceed by first loading the first page of those both sorted tables into main memory. And then I compare the tuples that I have in main memory in order to find matching tuples. And once I have done that for all the tuples in main memory, I'm loading the next page for one of the 2 sorted input tables. And I'm always loading the next page for that table where the last entry is the smallest, because maybe the next page from that page still needs to be matched against some currently loaded tuple from the other table. All right, and I keep doing this essentially until for one of the 2 input tables I have no pages left. At this point, I know that I have produced a complete join result and I can terminate. And here again, the algorithm is crucially based on the assumption that my both input tables are sorted once this phase starts, because otherwise I would miss potential join results. Now, here a little example about how I'm doing this. Now on hard disk, I have data for 2 tables, where the first table is a little bit larger. And as you see here, we have already executed the first phase on both input tables. That is why those tables are sorted. And I still have 3 buffer pages. And for this second join phase, I also need an input and an output. 2 input buffers here and 1 output buffer. And I start by loading the first page of each input table into the associated input buffer. So I'm doing this over here. And now I'm trying to identify matching tuples here. Now in this case, they don't seem to be any matching tuples. So I am first of all excluding that it can be any matching tuple with the minimum here. Then I'm deleting the minimum that I now have in main memory. No matches so far. Also no matches for the 3, so I'm deleting it. At this point, I have run out of input for the first table, so I'm loading data for the next page. And again, I'm looking at tuples in increasing order. So 4, no, there's no matches for 4. 6, no, there's no matches for 6 either. All right, at this point, my input buffer 1 has also become empty again. And so I load the next page. So I'm analyzing 8, no matches for 8, 9. And now I have a first match. And because here I have a tuple with value 9. So I assume that this value is the value in the join column. So the tuples with a value 9 match together. So I'm copying that to the join output. And here I'm loading the next page from both of the input tables. And again, I'm going over it. 14, no matches. Should load the next page from the first table. 15, no matches. 16, no matches. 17, no matches. I should load the next page. And here 25, no matches. I should load the next page. 26, no matches again. 29, nothing, and so on. So this is the principle how I merge together two sorted tables using their value in the join column in order to produce the join result. All right. One special case that I have not shown in the example, but that I quickly want to discuss is the case where we have the same value, essentially tuples that have the same value in the join column, and there's many of them in one table, so they extend across multiple pages of that table. Now, if you have that, if your first table contains many tuples with the same value in the join column, spread out over multiple pages because there's too many to fit on one single page. Whenever you load a new page from the second table, in order to be sure that you find all matches for the tuples on that page, you actually have to go back in the first table to the first page on which you find entries with the current value in the join column. So whenever you load a new page in the second table, you will have to go back a few pages and consider all the pages in the first table which have the same value in the join column. This case is rather atypical. Still, I mean, the implementations of sort-merge joins consider it, but if that case happens, then of course efficiency decreases because you have to read pages multiple times. So that makes this join more expensive. Now, in the following cost analysis, we will actually assume that this case does not happen. So we assume that each of those pages is read only once. And then the cost of this merge phase is essentially proportional to the number of pages in both input tables. And as before, we're not counting the cost for writing out the result of that join. And this is the overview of the total join cost. We have two input tables with M and N pages and B buffer pages. Then in order to calculate the cost for the first phase, we have to calculate cost for sorting the two input tables. So we just use the cost formula from the previous slide, and we use it once with M and once with N pages. So here in the second formula, by the way, I see that the argument of the logarithm that should be N divided by B instead of M divided by B. For the second phase, the cost is essentially the size of our two input relations, M plus N. And so in total, we have the sum of all of those components as total cost for the join. Now, the question is, how much main memory are we using in order to execute the join? Now, in the first phase, we are essentially trying to exploit all buffer pages. Essentially, the more buffer pages we have, the more sorted runs we can merge together in one step. And that means we reduce the number of steps if we can exploit more main memory. In the second phase, however, we only exploit 3 buffer pages, one for the first input, one for the second input, and one for the output. Now, this already tells you that maybe something can be improved, because here in the first phase, we are exploiting all main memory, while in the second phase, we only exploit a part of a main memory. And in the context of data processing, you can often speed up things if you're willing to use more main memory. So this is somehow strange, and it already gives us the feeling perhaps that maybe there's something that we can improve with this join operator. There is indeed something called the refined sort-merge join, which exploits that we actually have more main memory than we are using with this first version of the join operator. And the high-level idea of that join algorithm is that we can actually merge together more than 2 sorted tables in the second phase of the join, because we have more main memory available. So we can exploit that by not completely sorting the tables in the first phase of the join. So far, we assumed that those 2 input tables, they're completely sorted before the second phase of the join starts, but that is not really necessary. Now, if you don't need to sort the 2 tables completely, it means that we save a couple of passes over our data, and that means we are saving quite a few input like page read and write operations. So what we do with the refined sort-merge join, if we have enough main memory, is that in the first phase, we only sort data chunks that fit into main memory. So essentially, we're only executing the first step of the first sorting phase. So we just load chunks of data into main memory, we sort them, write them back to disk. We do this for the entire table, and afterwards we are done. So at this point, we have not completely sorted the table, but we have produced sorted runs of a length that is proportional to our main memory. And now in the second phase, instead of at the same time joining together 2 sorted tables, we essentially join together a number of assorted table fragments, a number of sorted runs from both input tables that is proportional to the amount of main memory that I have available. So when merging together those multiple sorted table parts, I'm reserving 1 input buffer for each of those sorted table parts. And if I do this, when having like the first page from each of those sorted table parts in main memory, then I can also efficiently identify the next matching tuple, so I can do the entire join in one pass over the data. Here a little bit more detail, and we're gonna discuss that in a little bit more detail next time. So we generally assume that we have B buffer pages, we have input tables with N and M pages. In the first phase, we load those chunks of maximum size, what fits into my main memory, B pages, we sort them, write them back to disk. And afterwards, when taking together both input tables with N and M pages, I will have a number of sorted table chunks that is proportional to N plus M divided by the buffer size. And then in the second phase, I will merge together B-1 sorted table chunks together, because I need for each one my input buffer and 1 output buffer. And if I can do this in one pass, then my total cost will be in total 2 times N plus N for the first phase, reading and writing once, and 1 times N plus N for the second phase, which is only reading the data once. All right, so I'm gonna stop here. We are gonna discuss the refined version of the sort-merge join in a little bit more detail next time. This is the last join operator implementation that we will see. And finally, we will compare those different join operator implementations together. Have a nice weekend and see you again on Monday.